Welcome to an example in which we're trying to see is there a connection between time the statistics students study per week and their final exam scores. So if this is the amount of hours statistics students study per week, and these are the scores on their final exam, is there a relationship? Specifically, is there a linear relationship? We tend to think so, right? Probably the more time you spend studying per week on average, the higher your final exam score. Let's see if the data bears that out. So this is the kind of question people want to answer in the real world, especially in the 21st century information age all the time, is the connection between two variables, time spent studying and scores. Is there a connection? We sure hope so. How do you study that kind of thing? We're finding the correlation coefficient R. If you go to your exam 4 notes here I am on the exam 4 notes. If you go on down to number 6, testing linear correlation. There it is. So I've already got a copy of it. In fact, actually, let me just put a copy right here would be an easy way to go for us. There we go. Okay, so there it is, linear testing linear correlation, number 6 from the exam 4 notes. Put the data in L1 and L2 and then do the linear regression t-test. So let's do that. So the first thing you do is you're going to put L1, L2, so put these numbers in L1, these numbers in L2. So step 1, put the data in L1 and L2. You know how to do that. So once you've got it in there, then you go to Stat and over to Tests. Go down to, what number is it? F, which is linear regression t-test, and hit enter. That's the test we want. And when you do, it'll ask you a bunch of questions. It'll ask you for the X list, the Y list, the frequency, and the funny looking B, which is a Greek beta, and a funny looking P, which is actually a Greek rho, not equal to 0, less than 0, greater than 0. Okay, and we're going to put in here, this will be L1, L2, this will be 1. It probably will already have L1, L2. If it doesn't, you can put a second 1 and a second 2. We'll put those in there for you. Okay. And those will pop in easy. Frequency 1, and we have not equal to 0, so we choose not equal to 0 there. Hit enter and calculate. Got it. Okay, and then it'll tell you your R value. Go on down to your R, and they want 2 decimal places, 0.73. And then here we're going to choose rho. That Greek, it looks like a P, but it's really a Greek rho. What that means is the true R. This is so the Greek R, this rho is a Greek R, rho is how you say it. Anyway, and it's the same as R, which means it's the linear, it's R, I'll say it's R for the whole world. The whole world population. So the Greek letters in statistics, have you picked up on what's going on with that? The Greek letters in statistics always represent the truth for the whole world, the whole population, right? Because that's what we want to know. We don't just want to know for these, 1, 2, 3, 4, 5, 6, 7 students. We don't just want to know for these specific 7 students, did more time studying help them get higher finals? We want to know, is this true for the whole world in general, right? That's always what we're going for when we do a statistics problem. Is there truth in general here? Does more time studying make you do better on stats finals in general for everybody in the whole world? Is that generally true or not? So Greek letters always represent the truth for the whole world population, whereas R itself is just the sample of whatever it was for sample of 7 students, right? It's just the linear correlation coefficient for just the 7 students. So English letters are just from a sample. So the English R is just from the sample. That's all the way through the statistics course. English letters are always used for just a sample, and the Greek letters are used for the whole population. All right, so what's the p-value? And then why we put rho, the Greek p, or the Greek r, the Greek p-r here, is because we want to know the truth for the whole population. What are we saying? We're saying for the whole world, there's no linear relationship, because if rho is 0, that means that's an R, that's a Greek R. There's no linear relationship. It's 0. Whereas if rho is not 0, then there is a linear relationship between time and scores, time studying and score on the final, right? That's what we're testing. If rho comes out 0, if there's evidence, and also remember, it's always weak evidence for HO and strong evidence for H1. So we assume HO is true, and if evidence is weak, we stick with our original assumption that there's no linear relationship, meaning rho is 0. The Greek R, the linear correlation coefficient is basically 0. If there's strong evidence, then we say no, rho is not 0. There is a linear relationship. It's not 0. There is a linear relationship. That's what we're testing. Well, what the p-value came out to be? The p-value came out to be let me write it down here. 0.0631. They want it rounded to 4 places. 0.631. 4 places. So, what does that mean? And how does that compare to the alpha level? Well, specifically, that P 0.0631, and the alpha level, which they say right there is 0.5. How do they compare? Well, our p-value is greater. It's greater. Which means what? There's too much of a chance of luck. So if, or I'm kind of running out of room where to write things here. How about I put it in over here? Okay, so if the P is low, then the HO must go away, right? But in our case, the P is not low, it's greater. So the P is not low, so the HO must not go away. You tracking with me? That's what happened. So we fail to reject the null. We keep the null. Our p-value was greater. Our p-value is greater. So what does that mean in the real world? That means, because you might say, wait a minute, this doesn't make sense. You're telling me R came out 0.73. Remember what R is? It's the linear correlation coefficient. That's what it is. It's a measure of how strongly these data points seem to fit in a line. Well, that's fairly strong evidence, right? 0.73. Remember, the R value goes from -1 to +1 with 0 in the middle. The closer it is to +1 or -1, the stronger the evidence is that the dots fit in a line. What dots? Well, I mean, if we graph these, if we took these data and these are X values and these are Y values, right? It says right here that the X list is L1 and the Y list is L2. So the X is L1, the Y is L2. So if I went over 14 up 100, over 14 up 100, and I put a dot there, and I went over 1 up 60, over 7, and I put a bunch of dots, how much would they seem to go in a straight line? How much would they seem to line up? Would the dots seem to kind of fit a line like that? Or would the dots just all be random everywhere, no line at all? Well, the R value tells us, you can graph it or you can just look at the R value. The R value is a measure of how much the dots seem to line up. And the closer it is to -1, it's a line going down. The closer it is to +1, it's a line going up. If it's around 0, it's not very good evidence of a line at all. Well, we got 0.73. It's about right here. So that's kind of close to 1. In fact, it's probably more like about here, huh? It's kind of close to 1. That's certainly somewhat strong evidence that these data, the dots seem to fit a line, right? But there's always the chance of luck, isn't there? Right? When you grab a sample of, what is this, 1, 2, 3, 4, 5, 6, 7 people. We just grabbed 7 students at random. And it seemed like the students that spent more time got a higher score in the final. Seemed like there was some evidence for that. But how strong? Maybe you could have just got a lucky 9 students who seemed to line up. Maybe there's a bunch of other students who didn't study at all and got a total A. And some other people that studied millions of hours and got a total F. Right? Maybe you just got a lucky 9 students when you did your sample. And really, overall, the truth of the whole world population, that's always what we want to know in the end, is that there is no linear connection, really. There really is not a linear connection. And you just got kind of lucky in the data you looked at. Maybe that's the case. What's the chance of luck? That's the p-value, remember? The p-value is the probability that the results are just luck. That's what the p-value is. So there's a 6% chance that this data, which ends up looking somewhat like a line, if we graphed it, how do we know? Because R came out close to 1, a little bit close to 1. There's a 6% chance that those dots came out looking like a line by luck, by random luck, which isn't a great chance. 6% chance of luck's not great, but it's higher than 5%. They wanted us to test at a level of significance, 5%, meaning they wanted only a 5% chance of luck, and we got a greater than 5% chance of luck. We got a 6% chance of luck. So that's just too high. So we are going to, the P is not low, so the HO is not going to go away. We're going to fail to reject the null, meaning we're going to keep the null, aren't we? We're going to keep the null and forget about the H1 down here. I'm keeping, which means we assume what? We're keeping there's weak evidence. The evidence is just too weak. There's too high of a chance of luck. The evidence is fairly strong, but not strong enough, not ironclad. It's a little too weak. So the evidence is weak. We're keeping the HO, which says, no, we're going to stick with our original assumption that the rho, the Greek R, is really 0, meaning there's really no linear relationship. If you have it, R came out 0.73, what are you talking about? Yeah, we think that might have happened by luck because there's a 6% chance that came out by luck, just a random lucky group of people, 6% chance, which isn't great, but it's higher than 5. They wanted a 5%. They wanted evidence less than a 5% chance of luck. So we're saying, no, we think really our original assumption that there's no linear relationship. The rho is really 0. The R is really 0. The Greek R, which is for the whole population of the world, is really 0. There's really no linear relationship. Evidence was too weak. All right, let's go through the possible answers here and see what we can see. Statistically insignificant. Yeah, that's right. Too weak. Insignificant. Right, that's right. Too weak. Significant. No. Significant. No. So it's one of those first two. Which one is it? To conclude, there is statistically insignificance to conclude that there is a correlation between the time spent studying and the score in the final. Thus, the use of the regression line is not valid. Right. That's it. Not valid. Regression line not valid. What's the other one say? Thus, the regression line is useful? No. No, that's the whole point. When in the end, when you determine that there's weak evidence, there's not strong enough evidence, so you're saying there's no linear relationship, then you cannot use the line equation. The regression line equation is not valid because the evidence just is not strong enough. It's insignificant. It's too much a chance of luck. 6%. So we come on down, and now they're asking for the R squared. If you go to your calculator, the R squared will show up for you. The R squared is, they want 2 decimal places, so I'm getting 0.73. oh no, I'm sorry, 0.53. I looked at R on accident. 0.53. What does that mean? Well, that's 53%, right? If you change that decimal to percentage. And what is it? 50% chance the regression line will be good. No, variation in the final is connected. It's this one right here. That the R squared value tells you how much of the variation in final exam scores is connected to the amount of time they spend studying each week. Yeah, in other words, if you think about it, go back up here. Whenever you compare two things in the real world, like time spent studying and scores, if they're connected, and they're somewhat loosely connected, more time spent studying gives you a higher score on the final on average. But that's not the only thing, right? There's also how smart you are at math, right? We all have different natural abilities at all things, at math, at reading, at driving, at mechanical abilities, artistic skills, social skills, on and on you go. So it's not just how much time you spend studying, it's also how good you are naturally at math thinking, logical thinking like that, mathematical thinking, let's say. Mathematical thinking, right? There's also your background. Maybe you've taken a ton of other math classes. And so you have a strong background. Maybe you haven't taken any other math classes for 20 years. And so, other things affect your score in the final other than just how much time you spend studying. That's one of the things, but other things affect it too. Well, okay, so time spent studying in the final, how much does it affect your score in the final? Well, that's what R squared tells you. R squared tells you, which is 53%, that's what 53%. Well, I can't say it better than this. 53% of the variation in the final exam scores. 53% of how well you do. 53% of how, maybe I can say it a little bit better, of how well one does on the final is connected to time studying. So 53% of how well you do in the final comes from how much time you spend studying. Other things affect the other 47%. But 53%, like a little more than half of how well you do on what one does on the final is from time studying. And then the other 47% is due to other things. That's what R squared tells you. How much of one variable affects the other. How much of time studying affects your score in the final. 53% of what you do on the final comes from your time studying. It's an interesting number. And then finally down here, they want us to come up with the regression equation. So that's just A and B. A and B. You'll see on your calculator, it'll say y equals A plus bx. That's how I know it's A and B. Just look right on your screen. You'll get the A. I'm getting 54.86. And the B, 2.93. They want those both rounded to 2 decimal places. It's the A and the B on your calculator. Y equals A plus bx. All right, that's the linear equation connecting how much time you study with what score you get in the final. Remember, this is X, this is Y. It said right here, L1 is the X list and L2 is the Y list. So L1 is the X and L2 is the Y. So time spent studying and scores, X and Y, are connected by this equation right here. Now it says on this one, use the model to predict the final exam score for a student who spends 7 hours per week studying. If you answered on part C, the use of the regression line is not valid, then D and E does not exist. Did we do that on part C? Yeah, we did. On part C, we said the use of the regression line is not valid. Why did we say that? Well, because the p-value is too high, the chance of luck, meaning we don't believe. We don't believe that these guys are connected. At least there's not strong enough evidence to make us convinced that time spent studying during average time affects final exam scores in a linear connection. We're saying no, the p-value was too high, the chance of luck was too high. So we're saying, therefore, you can't use the linear relationship. We don't believe there is a linear relationship. There's no linear relationship. At least there's not strong enough evidence to us that there's a linear relationship from this study. So you can't be using the regression line. So we say down here, D Any does not exist is what that stands for. Does not exist. Why? Because we can't predict the final exam score from how long you study, because we don't really believe there's a connection there. We can't just say how long you study predicts your final exam score. No, we said no up here. We said there's no linear, right here we said there's no linear relationship, right? We don't believe in that. So then we can't be using that linear equation to predict anything because we don't believe in it. All right, come on down here to H. This is important, real life, how they predict things and do stuff. Next, they want us to interpret the slope of the regression line. The slope, well, down here, because the p-value was greater than the significance level, it was, remember? P-value was 0.06 something. The use of the regression line is not valid. That's all we say. The use of the regression line is not valid. Remember, our p-value up here came out 0.0673. It was greater than alpha. Which means what? No linear relationship. Weak evidence. Evidence is too weak. No linear relationship. So we say because the p-value is greater than the level, the use of the regression line is not valid. And then say they interpret the y-intercept. Same thing. Because the p-value is greater than the level, the use of we can't be using anything from the regression line. His y-intercept, his slope. We can't use anything from that regression line because we rejected that. Right? We said, no, it's not a linear relationship. So there we go.